Welcome to the next lecture, students. In the previous lecture we have discussed about the variations in demand. In that variation in demand, so in order to meet those variations, demand, so we are applying some factor of safety that we have learnt in the previous session. See here, one more point I want to add is, see, if you are calculating maximum hourly demand is defined as 1.5 times of average hourly of maximum daily day. So whenever we are having different daily demands, so one day you will be having the maximum daily demand. On that maximum daily day, what is the average hourly? That means, so on a maximum daily day, if you are having total daily demand, that means daily demand means what? For 24 hours. So you will be having a demand for 24 hours. So average hourly of maximum daily means what? So if you are having total daily demand, so if this 1.8Q is for 24 hours, then it is not average hourly. If you divide it with 24, okay, if you divide it with 24, then it will become average hourly. So whatever 1.8Q, if it was given as total 24 hours demand, then you need to divide it with 24 in order to get the average hourly of maximum daily day. Okay. And also if it is not provided like this, directly they told that it is average hourly, then take it directly this as a Q. Average hourly means this is a Q, or else they may also say the hourly value of maximum daily, the hourly value, this Q, they may provide this Q. This average daily demand was calculated hourly. This average daily demand was calculated hourly. Then you directly take the average daily demand without dividing it with 24. See what is the statement provided in the question. Understand that. Is it a hourly value or is it a daily value? If it is daily value, then you need to divide it with R. If it is a hourly value, you can directly take it. That is the only simple thing you need to look at the question. Okay. Now, so after variation of demand, so you now know the water demand and you now know the population. Now there is another term that is called coincident draft. In water demand, there will be another term called coincident draft. See, coincident, so the name itself saying that coincidenting, so two things are coincidenting. What are those two things? Is normal demand, so whatever the demand we are having, domestic, industrial, institutional, so all those demands, so those are natural normal demands, and sudden demands like fire demand. So if the both comes together, then it is coincident draft. So both fire demand as well as this daily demand both comes together, then it is called coincident draft. Okay. So again there is a term called total draft. So total draft is defined like this. So maximum value of this coincident draft and maximum hourly demand, because in maximum hourly demand we don't add fire demand separately. Already maximum hourly demand is having fire demand inside it, so that is why there is no need to add fire demand to maximum hourly demand value. Only for maximum daily demand value we need to add the fire demand. Okay. Coincidental draft. Coincidental draft means maximum daily demand plus fire demand. Maximum daily demand plus fire demand is coincidental draft. Okay, so total demand or total draft. Total draft. So this is maximum of coincidental draft and maximum hourly demand. Maximum hourly demand. So this is total demand. So total draft or total demand is the maximum value of maximum hourly demand or coincidental draft. Okay, now this total draft, so the distribution system that means where we supply the water to the community, that is distribution system. The distribution system is designed for total draft. Very, very important bit. So the distribution system is designed for a total draft. Okay, so these are the things which we need to learn for gate perspective. So variation in demand is over. Now, so for finding the source sufficiency, we need population, we need variation in demand, and the last thing we need to know is the design lives of various components of the water supply system. The design life of various components of water supply system. Okay, let us see that. So by this topic, so this part, the first part is over, that is source part is over. So now we are going to the next topic, that is what are the different types of sources. So in the first topic we have learned the source sufficiency, the water demand. So whether how much water is needed for a community, that is what we have learned in the first topic. Now in the second topic we are going to learn what are the different kinds of sources, types of sources. What are the different types of sources we are having, like so surface source, subsurface source, what are the classifications, how to know the yield of that surface source or subsurface source. All those things we will learn in the next topic. Okay, so now first one, component. Design discharge, and design life. See, our component starts with the source. Source means it may be a reservoir, or it may be a dam, okay, or a barrage or a weir or a diversion structure, whatever it may be, it is on the source. Generally these components are very costly to build and needs lot of time and land. Okay, so that is why these components cannot be re-established easily. We cannot create a reservoir again and again. So it's a one-time investment for years together. That is why generally we keep the design life. The design life of this will be very high. So design life, we keep a design life of 50 years. Design life of 50 years, and we design it for a design discharge of maximum daily demand. We design it for a design discharge of maximum daily demand. It should supply a minimum amount of maximum daily demand every day. Okay, that is the design discharge. That is source. After source, who will come? After source, the intakes. So from source to the generally what happens is, source is a river. Source is a river. So whenever you construct a reservoir or a dam, anything, so there will be water coming into the dam. Okay, the structure intake means what? See, intakes means, see, the name itself says intake. So whatever the water which we are diverting into some channel or some reservoir, some pipe, some conduit, whatever it may be, it is intake. Okay, that is nothing but intakes. Intakes can be provided anywhere in the system. Intakes generally we provide on the river to allow the water into the reservoir. Intake we provide at the beginning of the conveying pipes to intake the water coming from the reservoir into the conveying mains or conveying pipes. So intakes are, the name itself says intakes. Okay, now it's a structure which takes water into the system where you want to send it. Okay, that is nothing but the intake. Intake generally we design it for, this is also attached with reservoirs and also attached with the conveyance pipes which are sending water from reservoir to the treatment units and all. So that is why here its design life is also more, that is 30 years, and design discharge is 1.8 cube. Maximum daily demand. Maximum daily demand. Here it is also maximum daily demand. And next, after intake, who will come? Pipes, conveying mains. So these conveying mains will transport the water from the reservoir, from the source to the treatment units, So here this is also designed for 30-year duration, and the design discharge is maximum daily demand, that is 1.8 cube. Maximum all will be designed for maximum daily demand, only few are designed for different discharges. We will discuss it. So after conveyance, so you need to send the water either by gravity if possible, otherwise we will send the water through pumps into the treatment unit. So next coming is pumps. See, generally if you look at the pumps and filters, they will get clogged because pump work on the concept of a impeller. Okay, so that is why generally what happens, because of the friction. So in pump the head has to be converted from velocity to pressure. So that is why, so there will be some friction inside the pump. So that is why, in order to nullify the losses, so because of this friction, so you need to send more. In order to get the maximum daily from the pump, you need to send more at the input, incorporating the losses. So that is why generally we send 2 times of the average daily demand. So 2 times of average daily demand as the design discharge of pumps. 2 times of average daily demand is the design discharge of pumps, and here the design life is 15 years only. Why 15 years? Because so pumps will get wear and tear. So pumps cannot sustain for longer durations, and it's a technical updations also come in pumps which can be incorporated. So when you keep the design life less, if you keep the design life 30 years, then you cannot update the system up to 30 years as you have designed it for 30 years. If it is 15 years, anyways of 15 years the pumps will get damaged because of this wear and tear thing. And at the same time technological upgradations also can be easily incorporated because we are dismantling and rebuilding after 15 years of time. So that is why generally pump, the discharge is more, as well as in order to take care of the friction and losses and all, we are keeping more discharge, and the period is also very less, 15 years only design period. Okay. And next is after pumping, that is treatment unit. After pumping, that is treatment unit. From pump, where it goes directly into treatment unit. So treatment unit, again it is designed for a design discharge. It is designed for a design discharge 1.8 Q only, and the design life is 30 years. Design life is 30 years, but only rapid sand filter in the treatment unit. All the treatment units are designed for 30 years and 1.8 Q except rapid sand filter. So except rapid sand filter. So rapid sand filter, again it is a kind of the same principle what we are using for pumps because of wear and tear. So rapid sand filter do rapid filtration. That is why generally we want to displace it frequently. We want to remove and replace it frequently. So that is only for rapid sand filter we will be keeping. For rapid sand filter, so for rapid sand filter it is 2Q, again it's the same principle, and the design life is 15 years only. The design life is 15 years. This is for rapid sand filter. Okay. And after this distribution system will come. So distribution system. So distribution system designed for what? Total demand. Not 1.8 Q, not maximum daily, or not 2 times of my average daily. It is total demand or total draft. And the design life is, it is also designed for 30 years. It is also designed for 30 years. And from distribution, at the same time from the treatment unit we send some water into distribution, as well as if there is a surplus amount of water, so the demand is fluctuating, right? So the demand may be less, may be more, but your supply is always constant because your systems can supply, for example, 50 million liters of water per day. If your system is capable of producing 50 million liters per day, so that means you are producing 50 million, but the requirement of the public, one day it may be 45 million and one day it may be 55 million. So, but you can only supply 50 million. So, whenever you get 45 million demand, so this 5 million liters you will store somewhere, and when you got 55 MLD demand, that day this 5 MLD also you will give from the external source. So, where you are storing the surplus water needs to be stored, then only it can be taken when there is peak demand where the system cannot supply that much of water. That is why we need distribution reservoirs. We need distribution reservoirs also. Distribution reservoirs. So that is the last one. Distribution reservoir. So distribution reservoirs, so they design for maximum hourly demand. This is the only component which is designed for maximum hourly demand, because so every day whenever see here the distribution reservoir, how it works. So morning 8 to 10 the demand is very high. So in that time no water will go into distribution reservoir, everything will go to the households. But during midnight, So nobody utilizes the water. So in that time, we will send all the water into the distribution reservoir so that it will help in the morning 8 to 10 when the demand is very high. Are you getting me what I am saying? So that is why the distribution system, distribution reservoir takes water on hourly basis. So wherever there is fluctuation, surplus and deficit is coming, in surplus will go into the reservoir, deficit will go from the reservoir. So that is why, so it works on the principle of hourly volumes. So that is why it is designed for maximum hourly demand. Okay, it is designed for maximum hourly demand. It is designed for maximum hourly demand, and here its design life is 15 years only, because see, it is costly to construct because you need to elevate the reservoir, and you need to construct lot of RCC. Okay, that is why, so here its construction is costly. So you can easily add one more reservoir whenever it is required. So it can be easily constructed when there is it is an elevated one. So that is why so easy to construct. So you can expand it easily. So whenever there is requirement is more, then we can install one more reservoir adjacent to it or anywhere else. So depending upon the requirement, depending upon the growth of the communities and all, because if you construct this elevated reservoir at one location, big reservoir, so it may not give that much water to all the sections of the localities. So if the same reservoir is divided into two and kept one side, one area, and keeping another surface elevated reservoir in another area, so it can easily cater the needs of the community. So that is why generally we expand it even whenever there is requirement. So that is why the design life is kept as 15 years only. Okay, so these are the different components and their design lives and their design discharges. So these are very, very important for the examination. You need to remember all these things. Wherever the design discharge is increasing, design life is decreasing, those things are also very important, much more important than the rest, because everywhere it is 30 year only. So that easy to remember. Everywhere it is MDD only, that is easy to remember. But the pumps and rapids and filters, it is changing, and the design lives are also changing. And if you look at the distribution reservoirs, these are the only things where we are using maximum hourly demand. Rest of all the locations, it is maximum daily or 2 times the average daily demand. That is why, so this thing gains importance in the examination. So you need to remember all these things in this manner. Okay, so this is all about the water demand topic or source sufficiency. Now let us discuss source types. So what are the different types of sources? And after discussing the types of sources, we will do the problems of the first topic, so previous problems, and then we will jump into quality characteristics of water. Okay, so sources. And conveyance. Sources and conveyance of water. Now, basic sources are of two types. Surface and subsurface. So surface sources are rivers, lakes, ponds, sea and ocean are also considered as surface sources, but generally we don't use them as a surface source here, so that is why we don't take that. So reservoirs, okay, so these are the different surface sources we generally use. Any streams other than this, there are some streams which are not rivers, which feed rivers. So those are like kind of streams, running streams. Okay, so these are all the surface sources. These are all the surface sources. So here what happens are in the surface sources, generally their quantum of water will be very high. But if you look at the quality perspective, quality is little less. So quality treatment is expensive if you take a surface water. Either if you take subsurface sources. Subsurface sources are nothing but the groundwater, wells, okay, subsurface sources. So groundwater, well, either it may be a tube well or open well, springs, infiltration galleries, and infiltration wells. Infiltration wells. So all those things comes under subsurface sources. All those things comes under subsurface sources. Here the quality of water, if you look at the quality of water, if groundwater means what? The water has, surface water has to go to the deeper layers of the earth's crust. So it has to pass through different layers of sand, different layers of soil, which acts like a filter media for these waters. So because of this filter media, so all the suspended impurities will get removed and you can see the clear water. So these days the groundwater is also completely polluted. So generally if you compare the quality between these two, it is little higher quality because of lack of suspended solids. That is the only difference. So if they are dissolved solids, if you look at the dissolved solids point of view, so there won't be any dissolved solids in the surface sources, but there will be lot of dissolved solids in this subsurface sources. These days dissolved solids are also playing a crucial role in the quality of the water. That is why generally even the subsurface water is not completely good water, wholesome water to consume, but in comparison with the surface source it is better. Okay, so these are the different sources we are having. Now, so we have no need of discussing elaborately what is a river, what is a lake, what is a river, perennial river, non-perennial river. So the perennial river is the river which is having a continuous flowing, that is perennial. Non-perennial means so intermittent flow. Somewhere in rainy season it will flow, and in summer season you might not observe that much of flow in the river. That is nothing but non-perennial rivers. Okay, so streams are the channels which feed the rivers, and lakes and ponds, these are channelized small water bodies, and reservoirs are the man-made water bodies. Okay, so groundwater, the water which goes from the surface to the ground, that is groundwater. And wells, again there are two types of wells. One is open well. So in the old villages you might see open wells. Okay, open well. See, the open well generally discharge will be high but the yield will be low. So open wells, generally in the summer season, many of the open wells will get dry. So yield, see here the discharge, more amount of water you can draw. Okay, but the quantum of water which is coming is less. So here tube wells generally we penetrate it into deeper crust. So the depth, if you look at the open well and tube well will be much more deeper, because in cities and all these days we are using tube wells only, in which you install a pump and you will pump the water. So these are the tube wells. So generally tube wells depth is very high. So though the diameter is less, here the open well diameter will be very high. Okay, whereas this diameter is very, very less. That is why the discharge will be less, but the yield will be high in tube well. Okay, so here in open well, discharge is more, yield is less. Whereas tube well discharge is less, yield is more. Okay, so this is the basic classification of open and tube well. Okay, now in springs, generally there are two types of springs we are having. One is artesian spring. So that means, see, when the spring is feeding water to the ground surface, so that means to a stream, for example, so this is the water table, so this is the ground level. Let us take this is the ground level. Okay, this is the ground level. So here this is the water table outside the ground level. Okay, so this spring, whatever the water coming out of the spring, it will feed the groundwater. So this is a natural outflow of groundwater at Earth's surface. Okay, so this is a natural outflow. So here, whenever the groundwater, so this is the natural ground level I am showing. So this is the groundwater level, and this is the water level outside the ground. Then what is happening here? So it is coming out. Of the ground. It is coming out of the ground like a jet. That is nothing but a spring. Okay. So spring generally it is of two types. One is artesian spring. One is gravity spring. One is artesian. Artesian means it is coming out with some pressure. That is artesian spring. And next one is gravity spring. Gravity spring means if it is coming out in gravity, so it is not coming out like a jet, it is just coming out like a gravity. So this is the gravity. So this is coming out, but it is moving down due to the effect of gravity. That is gravity spring. Okay, that is gravity spring. It is gravity spring. So these are the types of springs: artesian spring and gravity spring. So spring will feed the water. The spring will feed the water to the stream. So wherever the water table of spring is more than the stream. Okay. So infiltration wells and infiltration galleries, let us discuss. So infiltration gallery. See, infiltration gallery, it is nothing but a horizontal well. See, vertical, generally well will be vertical, having opening on the top and bottom. Okay, so why open in the top? To get the water outside the well. Why open at the bottom? To get the water from the ground. So well is simply a tube vertically standing on the ground at some depth. So similarly, if you roll it 90 degrees, if you make it horizontal, then it is horizontal well is nothing but infiltration gallery. So the cross section of infiltration gallery will looks like this. This is the cross section of infiltration gallery. So this is the intake. So this is adjacent water. Generally, this infiltration gallery, we keep it on the bay of a stream or a river. Generally, we keep this infiltration gallery along the shore of the river, along the bay of the river. So parallelly it runs along the river. Okay. So here, how to calculate the yield of the infiltration gallery? So let us discuss it in an elaborated way. Infiltration wells also I will discuss. Infiltration galleries also I will discuss separately. So these things are very important because water supply system will get water either from infiltration gallery or from infiltration well. If you look at any river nearby you, go and check. Either in that river there will be infiltration wells or there will be infiltration gallery installed in the river. So then only we can draw water from the river. Especially in cities, rivers which are moving in cities, there you might definitely find this. See, excuse me. So this is infiltration gallery. So if you look at the cross section, if you look at the longitudinal section, so this is the height of the water head. So this is the height of the water inside the infiltration gallery. So this is lengthwise, it is moving like this. If you look at the lengthwise, so this infiltration gallery will be lengthwise like this. Okay. Now, so what is the yield of infiltration gallery? Yield of infiltration gallery is equal to Q. So we have learned this in the soil mechanics. So Q is equal to KIA. Q is equal to KIA simply. So what is K? Permeability of the soil. Okay, permeability of the soil is K. What is I? I is the hydraulic gradient. Hydraulic gradient is nothing but head loss by length of travel, right? And this is the area. So if you look at this figure, what is the head loss happening here? This is the head before the entering infiltration gallery. This is the head after entering infiltration gallery. This is the head before entering infiltration gallery. This is the head after entering infiltration gallery. And the length of travel. So if you look at the length, so this is R. This is R. So R is the radius of influence. So this infiltration gallery, so how much radius it is influencing, that is R. Okay, how much radius it is influencing, that is R. So let us take this as R. So H minus H is the head loss. H minus H is the head loss, and the length traveled is R. So H minus H by R. So this is completed. The head loss, the hydraulic gradient term is completed. What is area? What is area? See, area means, so this is the traveling direction of the water, right? So water is traveling in this direction. So you need to take the area perpendicular to it, right? You need to take the area perpendicular to it. So now, what is the area I need to consider now? So this is a trapezoid. If you look at this, this is a trapezoid. H plus H by 2 is the area of this. H plus H by 2 is the area of this, and multiply with the length. So surface area. So here H plus H by 2 is a trapezoid, right? H plus H by 2 into L, length of the infiltration gallery. H plus H by 2 into L. This is the area of the total water which is coming into this. Okay, so if you look at this, K H square minus H square multiplied by L by 2R. So this is the yield of infiltration gallery when the water is coming only from one side. I am not considering this side. Only I am looking at one side. So I have did this proof by looking at one side. If I am looking at another side also, multiply it with 2. Okay. So when water is entering from one side. So if the water is coming from either side, it is double of this. So when water enters from both sides, okay, when water enters from both the sides. So let me repeat this once. See here, Q is equal to KIA. K is the permeability of the soil. Head loss is H minus H is the head loss, and the traveling length is R. Okay, so this is over. This is over. Now the area part. So area means the water is coming like this. So I need to take all the quantity of the water here. So this area into length. This area into length. H plus H by 2 into the length. Then you will get the total area of this infiltration gallery. So by doing that, we will get the yield on from when the water is entering from one side. So if you multiply it with 2, then you will get the formula for the yield of infiltration gallery when it is coming from either sides. Okay, so when it is coming from either side. Now this is infiltration gallery. So next is infiltration well. So generally infiltration well will be a vertical well closed at the top, open at the bottom. Infiltration wells are such that they are closed at top and open at bottom, whereas infiltration galleries are open at either ends, whereas the normal open well is open at either ends but it is vertical, whereas this infiltration well is vertical well only, but is closed at the top, open at the bottom. Okay, infiltration well. So general infiltration well, if you look at that, so this is the top and there will be water entering from the bottom. So here it is closed, the top is closed and the water is entered from the bottom into a infiltration well, and a series of infiltration wells are placed. Okay, these are the infiltration wells. So all these infiltration wells are connected to a main well that is called jack well. So this is jack well. So from the infiltration wells, the water will enter into the jack well. So from this jack well, the water will go to treatment unit. So from the jack well, the water will go to treatment unit. Okay. So this is very important bit you need to remember. So infiltration well is closed at the top, open at the bottom. The water comes from into the infiltration well like this. From this infiltration well, we will connect all the infiltration wells to a well called jack well. This is important. Jack well. So this jack well will feed this water into the treatment unit. Further thing will be done in treatment, and then we'll send that water into the distribution system. So these are the things we need to remember, we need to learn in the part of source and conveyance of water. Okay, source and conveyance of water. And now we will be doing the questions of this topic, okay, now in the next session, and then we will discuss the quality characteristics of water. Thank you so much.